Okay, we have studied functions of single random variables, and next we will look at functions of multiple random variables, but we will start this discussion by functions of two random variables. And we will start with a simple example. This distribution is the example we have been using, and we will use it again in this example, and we will define two new random variables, y as the minimum of x1 and x2, where the joint distribution of x1 and x2 is given here, and z as the maximum of the two. Okay, so what you will do is, well, since the distribution is discrete, y and z will also be discrete distributions. This will be nothing but the probability that y equals y, and y here is by definition the minimum of x1 and x2. Therefore, for x1, x2 pairs, I will just look at whichever is the smaller. So when x1 takes the value of 0 on this line here, okay, of course, certainly, since x2 is either 2 or 5, the smallest value will be 0. So with probability 0.4, the sum of this one and this one, um, y will take the value of 0. And when, again, I have these two, it's the pairs 1, 2, and 1, 5. So again, x1, which is 1, is the smaller value. So the sum of these, 0.3, will be the probability of y being equal to 1. For this and this, you see this one is 4, 2. So the minimum value is 2. So y will take the value of 2 with a probability of 0.12. And here we have the pair 4, 5. So the minimum will be 4. So with this probability, y will take the value of 4. And the distribution here is, as you can see, given. Okay. There are 4 values the random variable y can take: 0, 1, 2, and 4, and the probabilities are computed based on this joint distribution. Similarly, we can find the distribution of z. You see, when you are here, x2 is 5. Therefore, since x1 can take values only 0, 1, 4, when coupled with 5, the maximum of the two will always be 5. So add these three up: 0.24, 0.18, 0.18. Add them up, you get 0.6, where z is 5, the maximum value. Okay, and when you have this pair 4, 2, the maximum value is 0.12. So 4 has a probability of 1, 2. And here you have 0, 2, and 1, 2. In these pairs, the maximum value is 2. So you add them up, you get 0.28, which is the probability of z being 0.28. Okay, so this is how you compute the distributions of y and z. Now, at this point, maybe we can also define the random vector consisting of the components y and z. So maybe we are interested in the joint distribution of y and z. Remember, if I have the marginal of y and the marginal of z, it's not possible to write their joint distribution. But since I have the joint distribution of x1 and x2, looking at this, I can write the joint distribution of y and z. Okay? And remember the definition. Y will be the minimum of the two, z will be the maximum of the two. And in all but one of these pairs, 0, 2, 0, 5, 1, 2, 1, 5, and 4, 5. You see x1 is the smaller value, x2 is the larger value. So you see these 5 green points here. For the same outcomes, we have the same distribution. But for this pair 4 and 2, where x1 is 4, x2 is 2, the minimum is not x1, but x2, and the maximum is x1. So we will have this 0.12 probability, not at 4, 2, but at 2, 4. Okay, so this is the joint distribution of y and z defined through this function. Of course, if you change these functions, the minimum and the maximum, I have just selected these as example functions. You can define any function you like. Cosine of x1 times sine of x2, or x1 times x2, x1 minus x2, x2 plus square of x1. Anything you can think of, you can find the joint distribution of y and z in the same approach. Now we can generalize this if we define z as the maximum of x and y and w as the minimum of x and y. We would like to obtain the joint distribution of z and w in a general setting, not in that example, but in a general setting where we have the joint distribution of x and y. Okay. To write the CDF of z, the marginal CDF of z, we have, well, by definition, this is the probability that random variable z is less than or equal to parameter z, and random variable z is defined as this function, the maximum of x and y, okay? And since the maximum of x and y is less than or equal to the parameter z, this means that both of them, both x and y, are less than or equal to z, okay? So this defines, as you see, the CDF of x and y evaluated at the point z and z, because x is less than or equal to z and y also less than or equal to z. Okay, simple as that. So evaluate the joint CDF of x and y at point z and z, you get the marginal CDF of z evaluated at z. What about w? It's a little bit more complicated because the minimum of x and y less than or equal to w, it doesn't now signify a joint or an intersection event like this, but it signifies a union event. The minimum is less than or equal to w means either x or y is less than or equal to w, right? So this is a union event. Therefore, I will write this as probability of this plus probability of this minus the probability of the intersection. And probability of this is clearly the CDF of x evaluated at w. And the probability of this is the CDF of y evaluated at w, and minus the intersection, which is given here, which is equal to the joint CDF of x and y evaluated at w and w. Okay. So this is how you can find the marginal distributions of z and w. Alternatively, to find the marginal CDF of w, you can use another approach. You can compute its complementary CDF. Okay, instead of this CDF, you can compute its complement, which defines the event the minimum of x and y is greater than w, not less than or equal to, but greater than w. Okay, be careful here. I have strict inequality. Since the minimum is greater than w, that means both of them, x and y, both of them is greater than w. But this event I can now write easily because you see, it's this event here. This is w, this is also w, x and y exceeding w. But, well, of course, these boundaries are not included because strict inequality. Therefore, I can write this CDF as 1 minus this integral over this region. You see, w is not included in the integration because any probability I have on these lines will be included in this probability.